I know it's early, you probably all just finished your breakfast, but it's never too early to talk about pizza, right? Come visit with me a very special pizza shop, the Cloud Foundry API Pizza Shop. Today we're going to take a look what happens behind the scenes in the Cloud Foundry API through the lens of a pizza shop. Some requests are handled right away, others become background shops that need baking. That's where the CC workers come in, and that talk is all about how we've kept them baking more efficiently. My name is Johannes Haass. We're not talking about pizzas. I'm a software engineer at SAP. Most of my development time I spend on CF API related projects, so mainly Cloud Controller. I have approver roles in the app runtime interfaces and app runtime deployments working group, and have been working with Cloud Foundry now for more than 6 years, both as on the application side, but also many years now on the platform side itself. And yes, that's not a fancy B in my name, if you maybe notice. It's just a special German double S. Okay, this is the Cloud Foundry API Pizza Shop. So far, it's very empty, but no worries, it will fill up in a short moment. First of all, we need our ordering desk. That is our CF API endpoint. So every request, no matter if it's a simple one like CF orgs or CF spaces, or a complex one like CF push or CF marketplace, every request hits that counter. The requests originate by our users. Those are developers, operators, automated scripts, and so on. And of course, some users are nice. They do one request at a time, while others rather flood the system or hit the counter. But of course, our pizza shop needs to be able to handle all of that. Because we know that some operations like a CF push are a bit more complex, we handle them asynchronously. So we need some sort of counter where people can pick up those asynchronous tasks. And if we do something asynchronously, of course, we should also keep track of what we're doing. For this, we have our ordering system. This is basically our delayed shops table. And there we can then see what orders are currently there and what is the status of those. And of course, those orders then also need to be executed. For that, we have our baking section, so our chefs, and most importantly, our CC worker ovens. And those CC worker ovens then actually process those jobs, so they're baking the pizzas into real results. Let's go through the pizza shop with a concrete example. So we have here a customer, let's call her Max, and she does a simple CF push. I know, some simple Node.js app or something like this. And some things of a CF push, like some parts of a CF push are handled synchronously, like getting all the space details. So that's like ordering a drink. It will be directly handled at the request counter. But the actual push itself, like imagining uploading all the source code, that's more complex. So that will be handled asynchronously. And for that, we create a new order in our system. That will be now for Max, order number 20. She also receives a piece of paper with the order number, and we can see the order status is now pending. It has not picked up yet. Then Max will move on to the finished jobs counter to finish for her pizza. In the meanwhile, we can see that the status now of the order now changed, so that it's now in progress, and we can see that the middle oven is now baking that pizza. And a few moments later, the pizza is baked. Max receives the pizza, so the push is complete, and this order or this request is done. And this is the Cloud Foundry API Pizza Shop. As many of us use and operate it every day, it has been running for years, right? Orders come in, jobs get processed, pizzas go out, everything works, right? Well, not quite. Today I want to walk you through 4 particular challenges we've seen behind the counter and the improvements we've made to make the baking section even better. Our first challenge is training. As you can see, it's early morning. It's just after 8 o'clock. It's not it's not so busy at the store. But it doesn't matter if it's really rush hour or early morning. At any time, Bosch can walk in and say like, okay, time to update the oven. And that's where things might become messy. Of course, in the real world, pizza ovens run for decades. But in the CF world, Bosch would redeploy them because the locking library in the temperature controller has a CVE or something like that. So let's see what Bosch is doing. First of all, Bosch put a warning sign in front of the oven. that makes sense. So so now our chefs know, okay, don't use that oven anymore for making new pizzas. Use the other ones instead. That's good. But you can see there's also a stopwatch saying 15 seconds. And if you look at the oven, you see there's still one pizza in it. That must be this order number 19 by Ash, which we have been baking for the last couple of minutes. Maybe it's like a nice large deep dish service instance or something like that, which takes a bit longer. And let's see what happens after 15 seconds. Okay, now you see Bosch took out the pizza from the oven. That's probably not very good. Let's see what happens. Yeah, Bosch just threw away our pizza in the trash. And yeah, that's of course not good. Now our chefs need to prepare another pizza for Ash because we cannot send Ash home without a pizza. And of course, Ash now needs to wait longer. So yeah, that's not very good. And if you think about it, baking a pizza in 15 seconds, that's probably rather unrealistic. So let's tell Bosch rather to wait 15 minutes and say basically, Bosch, okay, when you do an update on an oven, wait up to 15 minutes. And if then there's still a pizza in the oven, then you can just throw it away anyways, because after 15 minutes, it probably will be burned. And then, no one wants a burnt pizza, right? And the problem here speaking in real CF terms, is that the CC worker used the Bosch Process Manager, BPM, for training. And BPM has a default train period of 15 seconds. And if you have long-running jobs, which exist in the CF API, this is not sufficient. So what we did is we implemented a custom train script for the CC workers with a configurable train period. And so operators can now configure this worker grace period. And the default is still 15 seconds, but we have set this to a much higher value in our productive environments. We set this to 900 seconds or 15 minutes. And this basically gives every job a chance to be finished before Bosch lifecycle operation is actually started. In addition to that, we also do now parallel training for each worker process to reduce the overall training duration. And we also ensure that we clean up pending logs, which helps, for example, if you reduce the number of CC worker VMs, that those pending jobs can be picked up faster again by a different worker. Okay, this was the first challenge. The second one, we'll focus again on the ovens. And imagine now you are the manager of this pizza shop. And of course, as manager, you try to run everything as efficient as possible, especially when it comes to cost. And when you look at those 3C worker and also at those 3 CC worker ovens, what do you notice? What do you notice? Yeah, they're empty, right? There's not much going on in those ovens. And what can we do about it? I mean, at the moment, it's early morning, we're just having one order in progress. So we don't really need that capacity. So my clicking. Okay, so sorry, somehow the animation was stuck. So we just get rid of one oven, then we've reduced our capacity, but we've reduced our oven cost by 1/3. And that's at the moment we don't need that capacity. That's all good, right? I mean, with this now we can bake 2 pizzas in parallel. That's still fine, I guess. But when I look at those ovens now, I still think there's a lot of empty space in them. I mean, we just put one pizza in them, and such a big oven, that's not very efficient. So why not use trays to bake multiple pizzas at once? So with this, we can now, for example, here we can now bake per oven 3 pizzas in parallel. So if you think about it, then now basically we've doubled our capacity. Before we had 3 ovens baking 3 pizzas in parallel. Now we have 2 ovens baking 3 pizzas each in parallel, so in total 6 pizzas in parallel. But we also reduced our costs by 1/3. So we did this without modifying the ovens. We just used some simple trays and made more use of the existing ovens. Speaking again in cloud controller terms or CF API terms, trays are actually threads. So what we did is we implemented a thread-based implementation of the CC workers. So in the past, the number of workers was determined by the number of CC worker instances or CC worker VMs, multiplied out by the number of worker processes running on those VMs. And with this thread-based implementation, we added a new scaling dimension to this. You may wonder why we did that. Well, we found out that most jobs which we're processing in the CF API don't require a lot of processing time. They rather are limited by I/O, meaning they need to talk to the database, they need to talk to service brokers, they need to talk to Diego, and all the other systems behind it. And we wanted to increase the throughput on a single worker VM while also reducing the resource consumption. And therefore, we came up with this thread-based worker implementation. And we also did some tests with that. So we compared 8 worker processes versus 8 worker threads. And the throughput was basically the same, but the memory consumption was 16% lower. So with this, it allows operators to run more workers on a single VM. And this is an optional feature which needs to be configured by operators. Okay, this was the second challenge. Let's continue with the third one. So far, we've mainly focused on the ovens itself, but let's also keep an eye on our customers. We can see here now one customer moved in. He is, let's call him Ben, and here has a list of many orders, or a long list of orders. Maybe he's ordering pizzas for his family or the whole conference audience, who knows. But I mean, still early morning, the ovens are empty, so no problem, we can handle that, right? So Ben in total placed 7 orders. With our current configuration, we can bake 6 pizzas in parallel, so all good. So therefore, 6 from his 7 orders are actually already processed. You can also see that Ben moved over to the finished jobs counter to wait for the pizzas. In the meanwhile, we can see that also the next customer already went to the request counter, that is Ari, and she also makes an order. She just orders a simple margarita pizza, nothing fancy. And of course, that order will be also noted in our ordering system. So far, so good. But because the ovens are occupied, this order cannot be processed at this moment. Well, then Ari will move on to the finished jobs counter, and there she will realize that she needs to wait. She needs to wait for Ben, because you could see in a way Ben is blocking now basically the whole system with his orders. So if you think about it, it's not very fair. So Ari now, she just wants her simple pizza. She now needs to wait. So that's not fair to her, and Ben is blocking everything for everyone. So therefore, let's add priorities to the orders. So what we do is we give the first order of a user the priority 0. Priority 0 means it's the most important, and increasing value means it's then less important. But for every subsequent order, we will decrease the priority. And so that means then Ben's first order has priority 0, his second order has priority 1, priority 2, and so on. Ari, on the other hand, only placed 1 order, so she will also get priority 0. And what we can see then is now that the execution actually changed a bit. Now from Ben's, only the first 5 orders are being baked, while also Ari's orders being baked in the meanwhile. And so this helps to make the whole system more fair, and so that Ari no longer needs to wait for Ben. And for Ben, anyways, it doesn't really matter, right? Because he has so many orders, he can only go home when all his orders are completed and not before that. Speaking again in Cloud Foundry terms, we call this dynamic job priorities. It's also an optional feature, and it basically does what I just described. It will increase the priority for each actively running job for a given user. And this prevents that a single user who creates many asynchronous jobs in a short time can slow down the execution for other users. And as I said, it's optional, but we at SAP have been running this now for over a year now. And it really helped to balance out the job processing, and it's helped us a lot to prevent delays for users on our side. Okay, let's continue with the fourth challenge. We already solved a lot so far, but even the best kitchen can break down if the ordering system itself cannot keep up. This is now a report of an actual CF API downtime we had in one of our productive foundations. In this case, a customer, let's call her Sid, placed an order, and that order triggered a few bugs. And suddenly, the entire board was filled up with thousands of orders, all from the same user, all with the same priority. The ovens, when we look at them, they were ready, right? There's a lot of free capacity, but they couldn't get any new orders in anymore. The ordering system was overloaded. But that's, of course, problematic for our kitchen. The kitchen no longer knows which orders to be processed. But most importantly, this is very frustrating for our customers because they no longer can get their nice CF flavored pizzas. So we basically have now a downtime of our CF API pizza shop. The actual problem here was that the delayed jobs table was overloaded. So the delayed jobs table is basically our ordering system. And there were some bugs in Cloud Controller that triggered more than 100,000 package deletion jobs within a few seconds. And then the query, which is used by those workers, by the CC workers, became very expensive. So that query is a select star from delayed jobs for update query. And especially this for update part makes this query very expensive because it results in row logs in the database. And then basically the query no longer, if there are that many entries in the delayed jobs table, the query no longer takes a couple of milliseconds, but rather multiple minutes. And if you think about it, we have more than 100,000 jobs in our table and can only process one every other minute, then it basically will take forever until all those jobs are completed. Well, how did we fix this problem? Well, the short-term fix in this situation was to restart the database, but the rather long-term fix were, of course, to get rid of those bugs that not so many jobs are created at this point. And we also improved the ordering system. How did we do that? Well, here are all the bug fixes related to that. I don't want to go too much into details here, but basically we ensure now that packages are marked as expired correctly and that we don't schedule package deletion jobs for Docker apps because that was the initial root cause that the user had a special Docker app, deleted that Docker app, and that then triggered this series of bugs. And yeah, we fixed all of those bugs. And then we also looked into the select for update query because we didn't like how expensive that query became or how expensive that query becomes if the database is under heavy load. And then we found out that MySQL is actually using a different logging approach, a more optimistic-based logging approach. This is also called log with read ahead. So basically, this is a query without this for update part. And if the delayed jobs table is under heavy load, this query is then much cheaper and reduces the load on the database. This is currently a feature flag in the in KP release if you want to use that for Postgres. So it's called log with read ahead. We've done extensive tests with that. It looks very promising, and we're actually rolling this out right now to our productive environments. But yeah, it's still in progress. So this was the fourth and final challenge. Let me wrap it up. We had our challenges. We had the problems with oven shutting down mid-bake. We had idle capacity. We had unfair scheduling. We had the overload of the ordering system, but we didn't stop at just observing those problems or work around them. We made the kitchen better. We have now a more robust ordering system. We introduced dynamic job priorities for fair distribution. We added the thread-based worker implementation to increase throughput while also lowering the resource consumption. And finally, we improved the training with a configurable train period. And we did all of this without expanding the kitchen, building the new kitchen. We just optimized what we already had available. With this, thank you very much for visiting the Cloud Foundry API Pizza Shop with me. I hope you had some fun. You can reach the people behind this feature in the KP Slack channel. And if you'd like to follow up or connect, you also find my contact information. Yeah, thank you very much. Any questions?
First to MySQL.
So the question was about if this this query optimization is also for MySQL. So as we only run Postgres, we've only analyzed this for Postgres, but we never saw it like we did some test runs and we didn't see a problem there with MySQL because MySQL doesn't, as far as I know, actually doesn't have this this for update part. So yeah, so basically there's also a lot of discussion around when you look at the delayed job community, what query to use, and there's no clear answer what is the right approach here. And for us, it seems to be this, the MySQL approach is actually also better for Postgres. But I think that's also something which we will find out in the long run, because we're still rolling it out, and then we'll still need to learn a bit from that.
Thanks. Thanks, Johannes.
Yep.